Good morning, and thank you so much for being here, and many thanks to the organizers, and in particular to Edward and Christian for inviting me. It's really a pleasure to be here. Okay, my name is Stefano Buzzi, and I work at the University of Cassino. And today I will talk about overcoming hardware impairments in cell-free massive MIMO by using differential space-time block coding. Okay, this is a work that is mainly carried out in collaboration with two people from my group. Marx Freitas, that is currently a postdoc, and Giovanni, that actually left a few weeks ago. He has been for 5 years in Cassino as an assistant professor, and now he's in Sweden as a senior researcher in Stockholm. Okay, this is the outline of my talk, brief introduction to cell-free massive MIMO in 6G. Then there will be the main core of the presentation about how to overcome some hardware impairments. In particular, I will talk about two different hardware impairments in cell-free massive MIMO by using differential space-time block coding. And finally, there will be the conclusions of the talk. So the first question that we want to answer is why do we talk about self-free and user-centric network deployments? And the answer was actually given about 10 years ago with this paper by colleagues that introduced the concept of self-free. And the idea is that I mean, even though massive MIMO is a big breakthrough, and I mean, it's how to say, one of the key technologies of 5G systems, the technology that has permitted a big boost in capacity with the possibility of multiplexing in the space domain many users using the same time frequency slot. On the other hand, it has been observed that it has large variability in performance depending on where the user is located. So if you are close to the base stations, you get very good data rates. Instead, if you are far from the base station or possibly at the edge between two cells, you are not so good performance because there is large interference from the other users. On the other hand, in self-free, if you deploy the antennas over the area, so instead of having one large antenna array collocated in one site, you deploy this antenna using a much cheaper access point, you can be more close to the user. And even if the user is served on average by a smaller number of antennas, it has a higher likelihood of being close to at least one access point, so much closer than in the case of the multi-cell massive MIMO. And so you have a performance that actually is more vertical. The CDF is more vertical. So all of the users get approximately the same performance. Okay, now there is this paper where we have explained why we think that self-free will be a big technology for 6G. In particular, we discussed about some enabling trends like supporting trends like ORAN and the AI, and some reasons why self-free will be important for 6G. I'm not going to discuss everything, just the fundamental reasons, because I want to move to the main topic, that is that of the hardware impairments. Okay, one is this uniformly grid service for everyone, that is the selling motto of self-free. I mean, taken from the title of this paper, as I was saying before. I've already discussed about this. You have a much better performance in terms of uniformity across users. Okay, there is less variance in the performance of the users, so better coverage. Much smaller probability of blockage, because if a user is served by more than one access point, of course, you have a macro diversity. And so the probability, even especially if you consider higher frequencies like millimeter waves or even the midband FR3, where blockages can be significant. If you are in a system with distributed antennas, you have macro diversity, so it's less likely that you have all of the links that are blocked. And another reason is, I mean, that self-free can be, I say, Mac ready, metaverse ready, in the sense that these days there is a huge quest for computing power, also driven by AI, by extended reality services, and so on. So there is a huge quest for computing power. And if you have a distributed MIMO system, so if you have distributed access points in the area, you can equip these access points also with some computing power. And so in the end, the network can become a big distributed computing and communication infrastructure. So self-free deployment with many distributed antennas and access point is ideally suited for the evolution towards of the network from a only communication infrastructure to an infrastructure that makes computing, sensing, and communication jointly. So that's another reason. It can be uplink centric. Again, if we think about the quest for computing or the new applications like extended reality or uplink video transmission, in a self-free with many distributed access points, we can have a greater amount of flexibility in allocating resources to the users, so that we can privilege some users that have a huge amounts of data to transmit in the uplink. And just to mention another of the buzzwords, or let's say major research area of these days, it's also very good if we want to do integrated sensing and communications, because if you have a large number of access points in your deployment area, you can, first of all, you can separate the transmitter and the receiver. So you can avoid the full duplex, the need to have a full duplex system if you want to do ISAC with a collocated system. So it's simpler to do sensing in this case. And also you can use the so-called target-centric approach, where you can say, okay, you can divide the access point in these joint groups, and these access points can take care simultaneously of the sensing of different targets in space. So you have a greater amount of flexibility with respect to the case in which you do sensing only with a collocated systems. Okay. After this introduction, I go and I pass to the main topic of the presentation, that is about hardware impairments in self-free massive MIMO. And in particular, I will focus on two different types of hardware impairments. Okay, the first hardware impairments, if we want to call it this way, is the technical challenge given by the need to make joint coherent transmission. Okay, because so consider this simple scenario where you have two access points. The channel on the downlink is H1 Hermitian from the first access point to the user. The other channel is H2 Hermitian for the second access point to the user. And if you want to do maximal ratio transmission, the ideal beamformers are the ones on the left. So you should have that W1 and W2 should be exactly equal to H1 and H2 in order to get a coherent gain that is given by the square magnitude of H1 plus the square magnitude of H2. Okay. But what happens? Actually, the access points have local oscillators to generate the radio frequency signal, and this coherent gain can be achieved only if the two phase oscillators in the two access points have exactly the same phase, which is actually very hard to realize. So if we take into account this effect, so the impossibility to synchronize the access point, then you have that the beamformers are actually multiplied by a random phase or by a phase that you cannot control. So in the end, the coherent gain will be not the one that you see on the left, but the one that you see on the right. write, and destructive interference may arise. Okay, so that's the problem that we are addressing here. Okay, now to solve this problem, there have been some over-the-air synchronization procedures have been proposed in the literature, and they are effective actually, but they are basically based on the estimation of this phase and on feedback. Some protocol that implies some exchange of information between the access points, and so in the end they can never achieve a perfect synchronizations, because even in ideal conditions, the estimates are corrupted by thermal noise. Okay, so they are quite complex, even though they have been demonstrated to work and to be implementable. And that's one solution. The other is to imagine that you have an optical synchronous fronthaul from the CPU to the access point. That is another possible solution. Here we propose instead the use of differential techniques. Okay, in particular, we leverage the theory of differential space-time coding that was very popular at the beginning of this century. Okay, now I have a just very brief introduction about differential space-time block coding, because I understand that this was a very popular topic when I was young, but I see here many young people, so maybe you are not familiar with this. Basically, what is space-time block coding is just a way of achieving diversity gains over a channel, introducing some sort also of repetition coding. The simplest example of space-time coding is the Alamuti code that actually was is a very popular code. Actually, Alamuti was the first to show that we could have diversity, space diversity, having only one antenna at the receiver. Okay, up to that time we used it to have diversity. We said, okay, we need two antennas at the receiver so we can get two copies of the transmitted signal with over the two antennas. Actually, with the Alamuti code, we can do this with only one antenna at the receiver. Of course, we need two antennas at the transmitter, which was good for the downlink where mobile user have only one antenna. So basically, what is the idea? The idea is that if you have to transmit two symbols, S1 and S2, you transmit them based on this matrix, okay? Where on the first column you see the symbols that are transmitted by the two antennas in the first symbol interval, and on the second column you see the symbols that are transmitted in the subsequent symbol interval. So here there is all the flow. So in the first symbol time, you transmit S1 and S2 from the first and second antenna respectively. In the subsequent time interval, you transmit the conjugate of S2 and minus the conjugate and S1. And at the receiver, it can be seen that based on this structure, you can have a linear processing that permits you to recover optimally the symbols. Okay, so in particular, the maximum likelihood rule to detect S1 and S2 ends up being linear, okay? But the drawback, if we want to say, is that we need to do this, we need to know H1 and H2 at the receiver, okay? So to avoid the need for the knowledge of the channel, differential space-time block codes were introduced, where basically what do? We again have this transmission matrix that is XT, you see it here, okay? But you don't transmit directly this matrix. What you transmit is actually CT that is given by the product of the matrix that you have transmitted in the previous time interval plus the current code word that you want to transmit now. And if you do this, this is what you are going to receive in time t-1, where you have transmitted CT-1. This is what you receive in time t, where you are transmitted CT. This product is CT. And you want to recover the code matrix. And actually, it can be seen that it can be done. and through a maximum likelihood detection rule. And in the end, the structure of the codes is such that in the end, you don't need, you can do the channel contribution simplifies. So basically you can recover the symbols without knowing the channel. It's just like when you do in one dimension with one antenna differential phase shift keying, where you encode the information not into the symbol that you are transmitting, but into the phase difference between the symbol that you are transmitting now with respect to the symbol that you had transmitted in the previous time interval, okay? So at the receiver, you can consider what you receive now times the complex conjugate of what you have received in the previous interval and get rid of the unknown phase of the channel. Here is the same, only the only thing is that we are doing this with multiple antennas and with multiple antennas, okay, and with multiple symbols. Okay, how can we exploit this? Basically, we can, because we say, okay, you had just showed a system where you have two transmit antennas and one receive antennas. How can we do this? Okay, we do this in this way. The idea is the following. We see here in this figure that we have many access points, and every access point has multiple antennas. Now, the multiple antennas from every access point actually are treated just like one antenna, if you think of the differential space-time block code. So I use these multiple antennas at every access point to get rid of the spatial, of the interference. So we do, we still use the multiple antennas to beamform the transmitted signal towards the user, okay? So we can do MMSC or MRT or partial regularized at zero forcing, whatever. So the system works in this way. We still perform as usual, as it happens in normal cell-free system, we still perform uplink channel estimation in the uplink, and use the channel estimate only to compute the beamformers to suppress the multi-user interference. Then each access point acts like a single antenna for the implementation of the differential space-time block coding technique. So in this case, we have a 4x4, a matrix that is 4x4, which means that we need 4 access points, or we needed 4 antennas. So you see that the matrix, the code matrix is given, the first row is given by one access point, the second row is given to this other access point, and so on. So these access points transmit to the user this code matrix, okay, in a distributed way. Each row is given to an AP that acts like an antenna in the original differential space-time block code. Okay, when we do this, we can do, don't need any longer the CSI at the receiver. We completely eliminate the problem of the phase misalignment. And of course, we have flexibility in AP selection because there are many space-time block codes. So we can decide to have that. We can change the number of AP that serve every user. We have flexibility because there are several choices for the differential space-time block codes. And okay, we can also compare with the PSK that is limited to PSK, because the other alternative is to directly transmit a differentially encoded symbols. And okay, the differential space-time block code, this is a little bit more complex, but decisions actually can be made independent for some code structure. Okay, I'll show the results for some simulation setup that you see here. In particular, we are considering 40 AP, 20 users, 4 antennas per AP, and 4 AP serving each user. So it's a user-centric deployment. We consider a modulation with cardinality 8. And okay, these are the results. Maybe we can focus just because, in the interest of time, we can just focus on the spectral efficiency, so the curves that are on the left. And okay, on the right, you see the CDF of the spectral efficiency. for the case of local partial MMSE or partial MMSE, two different types of beamformers. And the purple line is what you get in case the system is not calibrated. Okay, so basically you are not controlling at all the phase of the oscillators. The dashed line, the one on the right, is the ideal case where you have perfectly, I mean, the Gini-aided system where you have perfect synchronization between the access point, and the two lines that are the green and the dashed with the circle line, the black dashed with the circle, are the performance that we get with differential space-time block coding and with DPSK. Okay, so and we see that actually using differential techniques we get very good performance. Okay, I see 5 minutes. Okay, so I move to the other topic. Okay, regarding this topic, we have one published letter that is already appeared, and on arXiv there is a full journal paper that is currently under review. With regard instead to this other topic, this is just not yet published, not yet public information. We have a letter that are currently revising, so it's we will soon upload it on arXiv. And basically, the problem that we want to address is this of calibration errors, okay? Because another, an hypothesis that we usually rely on in massive MIMO and in self-free massive MIMO is that the channel is reciprocal, okay? So basically, the channel on the downlink and the channel on the uplink are one dimension of the other, okay? If you are in the same time coherence, channel coherence time. But actually, this is true only for what happens for the propagation, okay? From one antenna to the other antenna, okay? In the link between one antenna, the transmit and the receive antenna. In practice, there are the RF chains that introduce some hardly controllable coefficients that are reported here. So in the end, what happens is that the channel on the uplink and the channel on the downlink are not the reciprocal, one the reciprocal of the other, okay? So actually you have this problem. So the channel is not reciprocal. Now there are many papers that have considered the calibration. I mean, to do this, we need to calibrate the antenna array in order to have that all of these coefficients actually in the end become equal to 1 and have no effect. All of the papers have considered the calibration of the antenna array at the access point, but not at the UE, because at UE, usually the UE are taken only with one antenna. But if you have multiple antennas, like they have actually in practice, we should also consider the calibration problem at the UE. And we cannot use what the techniques done for the AP because it's a little bit more complicated because the UE are not controlled directly by the network. And so the techniques, the over-the-air techniques that are used for calibrating AP are not good for antenna, for the UE. So, but since actually here, I mean, this calibration error just introduce a modification in the channel, we can still use differential space-time block coding and get rid of their effect. So this is what we do. In particular, we assume here perfect calibration at the AP because we cannot compensate both the calibration error at the AP and the UE. So we assume that the AP have been perfectly calibrated through existing techniques, and we focus on the compensation of the calibration error at the UE. And these are the results. I'm just showing this plot. We don't need to focus on everything. Just to show, this is the spectral efficiency here. You see this line in the case of uncalibrated self-free. So this is what you get when UE are not calibrated. So you get a big penalty. These are for the case of perfectly calibrated. Okay, this is the ideal case. And this is what we are able to get with the use of differential space-time block coding, okay? The red and the blue is because we are using two different types of beamformers. So this figure here, the other are similar, shows you the gains that you can get by using this technique in terms of spectral efficiency. You can go from here to here, while the ideal case is this one. Okay, I jump to the conclusions. Okay, cell-free is is an interesting evolution of legacy massive MIMO and hopefully a key 6G technology. It was introduced almost a decade ago. For many years, people has just focused on seeing what are the gains that we can get with this technology and design beamformer solutions, power control algorithms for this strategy. But recently, people is starting to think, how can we implement really cell-free? And so the focus is shifting towards more practical questions, and hardware impairments are, for instance, considered. So we can hopefully say that the best is yet to come in this technology. And okay, that's all. Thank you for your attention.
Thank you for your talk.
Yeah, thank you very much for this interesting talk. I have several questions. The first one is, which type of user access point or RU assignment are you using in your simulation?
So which type of assignment? Okay, no, we are just using the heuristic assignment where we focus on the large scale fading. So every user is connected to the 4, in this case, access points with the largest value of the beta, the large scale fading coefficient.
Mm-hmm. Okay, thank you. And so in one of your simulations, I think when you compared the differential space-time block codes to the DPSK, it seemed at least...
yeah, it has better performance than the DPSK.
Yeah,
right.
Exactly. Yeah. So why don't you then use DPSK instead?
Yeah, actually, this is a good question. Well, I have to say that DPSK is limited to PSK, just to complex envelope modulation, and whereas with space-time block coding, you can also use QRM. This is one answer. The other answer is that okay, this is what we get here, but because this is not the usual achievable rate, because this is a sort of throughput computed as a function of bit error rate. So here we saturated 3 because we are using a 8 PSK, 8 modulation with cardinality 8. If we go to higher modulation, actually you observe better gains. But I mean, that's one. I mean, if you want to go for simplicity, that DPSK can be a good alternative. Mm-hmm. And but basically here, since we have LK equal to 4, we are using a space-time block code with 4 transmit antennas that has a code rate of 3/4. So here we get the penalty of the code rate. That's one big
right.
Alamuti doesn't have this problem because the code rate is 1, but Alamuti is the only code that has rate is equal to 1.
Yeah, thank you very much.
Just one question. So you considered orthogonal space-time block codes, but they are also quasi-orthogonal space-time block codes.
No, orthogonal.
No, they are also, yeah, but they are also quasi-orthogonal.
Yeah.
So which reduce the impact of this rate loss due to the half rate, or here you have a rate loss of 3/4. Did you also consider these kind of quasi-orthogonal?
Yeah, this can be a good idea for further research on this. Okay. No, we just considered orthogonal space-time block code just to simplify the detection rule and just orthogonal.
Okay, thank you.
Welcome.